Imagine a cosmic event so powerful, so cataclysmic, it outshines every star in our galaxy. A beacon of energy so intense it can be seen across billions of light years. These are gamma-ray bursts, or GRBs. These are the universe's ultimate light shows, fleeting moments of extreme energy release, brief, terrifying blasts of high-energy radiation, the most energetic form of light in the cosmos. They originate from distant galaxies, often billions of light years away, marking the death throes of massive stars or the collision of neutron stars. Thankfully, they're far away, their immense power diminished by the vast distances they travel. Because if one were aimed at us, if our planet found itself in the direct path of one of these beams, the consequences would be catastrophic. GRBs were discovered by accident during the Cold War, a serendipitous finding born from the tensions of the era, when satellites searching for nuclear tests, designed to monitor potential violations of the Nuclear Test Ban Treaty, detected mysterious flashes from deep space. It took years to realize these were new, bewildering astronomical phenomena, not of terrestrial origin, but from the depths of the cosmos. If Earth were hit by a GRB, it wouldn't be a Hollywood explosion, a fiery spectacle of instant destruction, but a silent, drawn-out disaster. The initial burst would last minutes, a seemingly short period, but its effects would unfold over years, a slow burn of environmental degradation, altering our atmosphere and biosphere. GRBs remind us how vulnerable our planet is, a fragile oasis in the vastness of space, in a violent cosmos. Studying them isn't just academic. It's not merely an intellectual exercise. It's about understanding our place in the universe, our cosmic neighborhood, and the threats beyond our world. So let's journey into the heart of these cosmic behemoths, these powerful and enigmatic events, and explore what science tells us about this ultimate, if unlikely, doomsday scenario. So what exactly is a gamma-ray burst? What are we really talking about when we use that term? In short, it's a flash of the most energetic light in the universe, gamma rays. Imagine a sudden, brilliant burst, far brighter than anything we can experience on Earth. These bursts unleash more energy in seconds, releasing an unfathomable amount of power into the cosmos. In fact, they unleash more energy in seconds than our Sun will in its entire 10 billion-year lifetime. It's a truly staggering comparison that puts the sheer magnitude of these events into perspective. Unlike a light bulb, which radiates energy in all directions, this energy is focused into two narrow beams, like incredibly powerful spotlights. This focused emission makes them appear like cosmic lighthouses, briefly illuminating the vast expanse of space. GRBs come in two main types, categorized by their duration and origin. First, we have long bursts, which are typically associated with the collapse of massive stars at the end of their lives. These are some of the most luminous and powerful explosions in the universe. Then there are short bursts, which are believed to originate from the collision of neutron stars or the merger of black holes. These events are incredibly violent and release a tremendous amount of energy in a very short time. The light from a GRB travels billions of years across the universe, traversing unimaginable distances to reach our telescopes. This ancient light has been journeying for eons before finally reaching us here on Earth. Because of the vast distances they travel, observing GRBs gives us a glimpse into the violent past of the universe, allowing us to study conditions that existed billions of years ago. The initial flash, the first sign of a GRB, is called the prompt emission. This is the most intense and energetic phase of the burst. This is followed by an afterglow of less energetic light, a gradual fading of radiation across the electromagnetic spectrum. This afterglow includes X-rays, visible light, and radio waves, each providing unique information about the burst and its environment. This afterglow can last for days or even weeks, allowing astronomers to study the event in detail long after the initial flash has faded. By carefully observing the afterglow, astronomers can pinpoint the burst's origin with incredible accuracy, revealing the location of the event in a distant galaxy. GRBs are not just powerful, they're also rare and fleeting events, making them all the more precious to astronomers. Each burst offers a unique window into the universe's most extreme and violent events, providing invaluable insights into the processes that shape the cosmos. Each one is a cosmic message from the distant past, carrying information about the conditions that existed in the early universe. By studying them, we unlock secrets about the life and death of stars, gaining a deeper understanding of the stellar life cycle and the evolution of galaxies. They're the universe's way of showing us, in the most dramatic fashion possible, just how wild, energetic, and dynamic it can truly be, constantly changing and evolving on a cosmic scale. Let's delve deeper and see how these titanic explosions are actually made, exploring the fascinating processes that give rise to these extraordinary events. The sheer power locked within a gamma-ray burst, or GRB, is almost incomprehensible. It represents some of the most energetic and cataclysmic events known in the universe. The energy behind a GRB comes from the most extreme events in the cosmos, releasing more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. These events are truly awe-inspiring. Long GRBs, the more common type, typically start with a massive star, a true behemoth in the stellar world. These stars are at least 30 times the mass of our Sun, dwarfing our own star in both size and energy output. They live fast and die young, burning through their fuel at an incredible rate. As these massive stars reach the end of their lives, they begin running out of fuel. The nuclear fusion reactions in their cores start to slow down. Without the outward pressure from fusion to counteract gravity, its core collapses in on itself, forming a black hole, an object with such immense gravity that nothing, not even light, can escape. While the core implodes, the outer layers of the star fall inward, forming a spinning, superheated accretion disk around the newly formed black hole. This disk is a chaotic maelstrom of matter. Magnetic fields, twisted and amplified by the black hole's rotation, funnel matter from the accretion disk into two incredibly powerful narrow jets, aligned with the black hole's poles. These jets blast outward at nearly the speed of light, carrying an immense amount of energy and matter. They are among the fastest moving objects in the universe, and these focused beams of energy and particles hurtling through space are what we detect as gamma-ray bursts. The jets don't stop there. They punch through the star's outer layers, blasting stellar material into space at tremendous speeds. Short GRBs, on the other hand, have a different origin story. They are born from the collision of two neutron stars, incredibly dense remnants of dead stars, or the merger of a neutron star and a black hole. These mergers create a kilonova, a powerful explosion that is less energetic than a supernova, but still incredibly bright. Kilonovas are also the primary sites in the universe for forging heavy elements like gold and platinum, elements that are far heavier than iron. Just like long GRBs, these mergers also launch intense jets of gamma rays, albeit for a shorter duration. Both types of GRBs, despite their destructive nature, are cosmic engines of both destruction and creation, playing a vital role in the evolution of the universe. They reshape their surroundings, scattering stellar debris and heavy elements far and wide, seeding the universe with the building blocks for new stars and planets. Each burst is a brief, spectacular finale, a fleeting moment of intense energy and light that marks the end of a stellar life or the collision of cosmic titans. It's the ultimate swan song to a star's life or a stellar collision, a dramatic display of the universe's raw power. Now let's take a moment to consider the implications. What would happen if one of these incredibly powerful bursts was aimed directly at Earth? Imagine a GRB aimed at Earth from a few thousand light-years away. There'd be no warning. The gamma rays would arrive at light speed. The sky would erupt in an eerie, blinding glow as gamma rays ionize the atmosphere, making it fluoresce. The flash would be brighter than the sun for seconds or minutes, temporarily blinding anyone looking up. The heat could ignite fires across continents, creating a global firestorm. But the biggest immediate threat, technology. The gamma-ray pulse would generate a massive EMP, frying satellites and power grids, plunging us into darkness. In minutes, our modern world would be thrown back centuries. And that's just the beginning. The real danger comes after the flash, the destruction of our ozone layer. Gamma rays trigger chemical reactions, creating nitrogen oxides that shred ozone molecules. Up to 75% of the ozone could vanish, letting lethal ultraviolet radiation flood the surface. The sky would turn brownish from nitrogen dioxide, dimming sunlight and causing a brief cosmic winter. But the real threat is UV radiation. It damages DNA, causes cancers, and devastates crops and plankton. Sunburn would happen in minutes, and the base of the food chain, on land and in the oceans, would collapse. The aftermath would be a world exposed to deadly sunlight. With the ozone gone, ultraviolet radiation would devastate life on Earth. Plants would wither, crops would fail, and forests would die, leading to mass starvation. In the oceans, phytoplankton, the base of the marine food web and a major oxygen producer, would be wiped out. Acid rain from nitrogen oxides would poison soils and water, making recovery even harder. The collapse of agriculture and marine life would trigger a mass extinction. Only underground or deep-sea species might survive. For most life, including humanity, the outlook would be grim. The very sunlight that once gave life would now bring death. This isn't just science fiction. Some scientists think a GRB may have triggered the Ordovician-Silurian extinction 445 million years ago. Most life then was in the oceans, and the extinction pattern fits a sudden UV radiation surge. Surface species died, deep-sea life survived. The event also saw a rapid ice age, matching the cosmic winter a GRB could cause. There's no direct evidence, no crater or iridium layer, but the circumstantial case is strong. Other theories exist, but the GRB hypothesis reminds us Earth is shaped by cosmic events. Our planet isn't isolated. It's part of a dynamic, sometimes violent universe. Studying ancient extinctions through astrophysics opens new ways to understand life's history. Sometimes the death of distant stars can change the course of life on Earth. Despite decades of study, GRBs remain mysterious. We know the basics: collapsing stars, merging neutron stars. But the details of how jets form and focus are still being unraveled. GRBs come in many varieties. Some are bright, some are dark, some have complex light curves. Scientists are still figuring out what causes this diversity: star mass, rotation, magnetic fields, or galactic environment. We're also learning how common GRBs are and how tightly their beams are focused, which affects the risk to Earth. New telescopes and the discovery of gravitational waves from neutron star mergers have revolutionized our understanding. These events are cosmic factories for heavy elements, like gold and platinum. Multi-messenger astronomy, combining light and gravitational waves, is opening new windows on the universe. Each discovery brings us closer to understanding these cosmic giants. So, what are the odds of a GRB hitting Earth? Incredibly low. Maybe once every few 100 million years, and only if the beam is pointed right at us. No nearby stars are poised to threaten us, so you're far more likely to face everyday risks than a cosmic death ray. GRBs are high consequence but extremely low probability events. Still, studying them is vital. They're natural laboratories for extreme physics. GRBs let us probe the birth of black holes, the death of stars, and the conditions of the early universe. They remind us that the cosmos is dynamic, violent, and creative. Our fascination with GRBs is about understanding our place in the universe. While we can rest easy, the quest to understand these bursts will keep pushing the boundaries of science. Each fleeting flash reveals a little more of the universe's deepest secrets.